Ito lemma and stochastic calculus. You can click the link below, and you will find my channel about fixed income securities, and then there is a content about stochastic calculus. You can just take those classes. You can just watch those videos, because I just don't want to repeat same content again. In addition, I will review stochastic calculus in offline class. Anyway, in the fixed income class videos, you can find the following videos and watch them, like fixed income 9, 10, 11. So here we have 9, 9-1, 9-2, 9-3, 9, 10, 11. This seems a lot, but they are all short, not that long. So I think you can take those lectures from 9 to 11. Okay. And then after you watch 9, 10, 11, you can jump. You can jump and you can watch 15 about live market model 1, 2, 3. So here you can go 15, you can jump to the 15. You have 15, 1, 2, 3, and you can watch those three. So if you watch those videos, I think you can get some basic knowledge, maybe not a detailed knowledge, but intuitive knowledge, intuitive understanding about some stochastic calculus. Anyway, the above, of course, if you have taken my class about fixed income securities, you do not have to watch our videos. But if you didn't, I recommend you to watch them. Alternatively, you can find other internet sources for stochastic calculus, and there are a lot of good classes on the web about those stochastic calculus and the basic financial engineering. By the way, all those things are part of my channel. So if you click this one, there are some channels about Python introduction, Python introduction, and those things. Channels. Channel is playlist actually. Playlist, Python introduction, and fixed income securities. There are many channels, but many playlists actually. So it is the fixed income securities over here. Okay, and about our class, we have a playlist for term paper format that you are already familiar with, and Python introduction, which include current classes. Okay, so playlist. Let's close, and let's close. My channel, not my channel, sorry, my playlist. My channel, part of playlist in my channel. Okay. Now suppose you took all this class or basic understanding about stochastic calculus, and let's go directly to the Ito lemma practice, and then I got many practice problems from this link. Okay, from this link, and from this link we have a good explanation and some examples. So I recommend you to go through this one. Okay. Alternatively, I can explain one by one. So I'm assuming that you took those classes. Okay, you took those classes, and let's go directly to the problems. So if you don't know anything about stochastic calculus, then you will not understand what is going on right now. Okay. Now let's go directly to the problems for stochastic calculus. Now suppose we have yt equal t squared wt third, and t is greater than 0, satisfy this one. Okay. Suppose we want to prove that when yt is this way, dy looks like this. Okay, dy looks like this. Okay, we wanna prove this one. So let's do it. MS Paint. Okay, so again. Okay, so yt is t2 wt3. Y is t2 wt3. Okay, looks like this one. Yt. We need time subscript. Time subscript over here. T over here. And what is t? T is just like number, actually time. And wt is Brownian motion. Okay. So t here, t is time, and wt is a Brownian motion. And now we want to calculate dyt. Okay, we want to calculate this one. So in order to solve this one, we have to do Taylor series expansion. Okay, Taylor series expansion. So, well, Taylor series expansion. So, first, let's take derivative of y. So, actually, we can call this one as f t wt. Okay, so first, we can calculate ft. Take derivative with t. So, it is 2t wt third. Right? Now, we calculate w. W take derivative with the Brownian motion, then it's 3, right? We have this term. So 3 and t square wt second, right? And let's do second derivative, which is, now we take derivative again, then it's 6 t square wt, right? So now we can do Taylor series expansion. This is ft. The change of y is, first we have to consider change of time. Then we have change of Brownian motion. Change of Brownian motion. And because it's stochastic calculus, we have to do up to second order derivative. WW and DW, change of Brownian motion square. Okay? And then because dw square, since dw square is dt, I proved this one in the lecture videos I recommended. So we can just plug this one. Then it is a 2t wt3, and then, okay, and then we have dt. Now plus, okay, plus w, 3t square wt square dw, right? And then plus 2 to the power of ww, so we have this one, 6t square wt, and then dw square dt. So we have same dt over here. So we plug this one over here, right? So then we have 2t wt third plus 3t square wt and dt plus 3t square wt dw. Actually, this is almost perfect. This is done. So let's check the answer. Wow, the answer looks like this one. So we put this one in terms of y actually. So y is this one. Y is this one. So we use this y. So this is 2 yt and then t plus 3. Now this is yt double t square dt. So we have actually this one. So actually 1/3. There was 1/3. Actually, so this yt, so 2, so well, this is another way of writing down. So we have three yt, actually t, let me, okay, so here yt 1/3, and t square yt 1/3 to the 3, right? Because 1/3 it becomes this one. So I think there is a small problem in this solution. So I think that my solution is y dt plus now t squared, so 3. Oh, 3 and again 2/3, right? 2/3, 3, and then yt 2/3. Okay, then dw. So we are done. Okay, we are done. Yeah. Yes. So this is solution. So we have, right? We have this term 2t wt third, and the 3t square wt square. Actually, sorry, 2t. So yeah, 2. This term w. Sorry. So it means that I have made error. So yeah, there should be w. Yeah. So I have a mistake because yeah, I have to put this one over here. So, and then half of this one 6t square. So 3. Yeah, 3t squared wt. Right. So I think my answer is right. So this one is the same to this one. So we can derive the solution like this one, right? Next, let's go to the next problem. Now, let's w looks like this Brownian motion, and actually let me, yeah, looks like this one, and then xt looks like this and satisfies Stochastic differential equation, and then what we want to prove is that when xt is given, we want to show this one looks like this one. So this is basically change of xt from 0 to dt, right? 0 to dt. So we want to prove this one, okay? So our idea is first we want solve this one. So here, actually, I wanna move this one. Okay. So here, so let me close this one. Capture. So let me capture this one and explain one by one. Capture this one. And here, and let me explain. So, well, we want to calculate first change of x, right? Change of x. Okay, we want to calculate this one. So basically, if you take a look at this, it is in some sense a change of x, right? Change of x from 0 to t. And how to prove this one? Okay, how to prove this one? So yeah. So basically, this is we have to know the intuition first. So basically, what this means is the xt minus x naught is basically change of x from 0 to t, right? 0 to t. So that's why we are interested in dx, right? Change of dx from 0 to t. So dx, because x is given, dx should be look like this. So again, we want to do the same thing. So we regard this as the function. This is a function of w and x. So let's write down xt is time function of time and w. So first we need to calculate ft, take derivative with respect to time. So we have two components over here. So time has two components, the first part and second part. So we have the take derivative with t separately. So about first time, if we take derivative of the first term, then it is minus alpha, right? Minus alpha e minus alpha t, and then these parentheses, right? Same. This is same to this one. And now we want to take derivative of second term plus e to the minus alpha t, and we want to take derivative of this term, right? Take derivative of this inside the parentheses. Then if we take derivative of x naught, it is just constant. And if we take derivative of this one, this is pretty easy. It is integration. So integration is inverse of differentiation, as you know. So if we take derivative, then we have just this part, right? So this part. So if we take derivative, then we have sigma, and we write down same thing, e alpha t, right? Alpha t dwt. So we are done. Okay. So ft looks like this. Okay. And then if we write down, and then if we take derivative of wt, well, it is all integrated out. So well, it is not function of wt. So we wanna write down more clean way. So if we write down more clean way, then this is clearly okay. This inside of this part. So you know this part is exactly the same to xt, right? So it is basically minus alpha xt plus e to the minus alpha t, and then dwt, right? And then dwt. Actually, we don't have dwt, and then of course we want to change up this one. So ft dt is simply minus alpha xt dt, and then plus zero plus, well, this is the, let's move over here. dt is simply now e alpha xt. So e to the minus alpha t sigma e alpha t dwt. So already we have changed. So we leave this one as it is, right? As it is. And then this term is exactly the same too, right? If we compare this one, this is solution. So this term is same to this one, right? And then this term is actually same to this one, and this term becomes this one because they cancel out. So minus alpha xt dt plus sigma dwt. We got this one. And then, so we want to calculate the dw, then fw, and then you can see this x function. We take derivative of fxt with derivative dw, Brownian motion, but as you can see, this is not a function of Brownian motion, right? So we have, it is not a function of w, so basically we did 0. So we, which is take derivative again, is still 0. So we have this one. Okay, so therefore we get the solution such that dxt looks like this one. So now we plug this one over here. So this is now we are integrate 0t, and then sigma dwt minus alpha xt dt, right? And we want to do the integration about this one, and then this one, then we have, this is same to sigma from 0t dwt minus alpha xt dt. Actually, because we have the same t, so you can, let's write down this one as from 0 to t. Now this is the sigma from change of x wt minus w0 minus alpha 0t x s ds. Now since w0 starting point is 0 in Brownian motion, we have a sigma wt minus alpha 0t x s ds. Okay, so this one is same to this one. Therefore we have xt equals x0 plus sigma wt minus alpha 0t x s ds. So this is the answer. So we proved this one. Okay, so this is done. Now let's move to the next question. Show that a is some real number, and then now we have two processes, z1 and z2, and defined by this way, and then we want to prove the systems of stochastic differential equation. Looks like this, right? So, well, let's prove this one. So let's open another file. So z1. So z1 is what? g1 is cosine awt, and z2 is sine awt, right? Sine awt, right? And then we want to solve such that easy, but to remind you the mathematics, what this requires taking derivative of cosine function and sine function, and cosine, take derivative of cosine function is minus sine x, And then if you take derivative of a sine function, it becomes a cosine function. And then we will use this one. We will use this one. Okay. So we have dz. Now, convenient thing is ft. Okay, write down ft dt plus write down formula fw dw. This is not formula actually, it's a Taylor series expansion. f2w dw square. But here we know ft is 0, right? So this is fw. So what we have to calculate is, okay, first take derivative of z1 with respect to the w. Then it is cosine, so it is the, because there is a, so we have minus a sine a wt. All right, and then the z1 dw square, we take derivative again, so minus a square. Now cosine a wt, right? And then we can do the same thing. The z2 dw is sine, so it is the a cosine aw, and if we take derivative again, dw square, this is now minus a square sine aw, right? Now we can plug this one over here. We can plug this one into over here, so we can get equation for dz1 and dz2. Of course, we will impose wt dt. All right. So we can plug dt term together and dwt. Then we will gonna have solution something like this. dz는 dzt1 is a sine a dw and half of a square cosine w dt, which is basically, yeah, if you compare this one over here, solution over here, actually, let me write down. So change the color. So therefore, dz1 equal, we have minus a sine aw dw plus, actually now, yeah, we have minus and the half of a square cosine aw and dt, right, with this one. And then d2, we have this one, so a cosine aw dw and minus half of a square sine aw, because we have dw term, dw square, so it is dt. Okay, so this is exactly same to this part. So now we can solve this one together. Then you can combine this together. Then we will have something like this. Now, since we have something like this, we can do the integration. Then we will have this equation. Okay, Professor out.